Okay. All right, as I said, since we're doing all this angle talk, we better make sure we understand about angles. So let's think about angles some more. And for angles, computing angles, we'll finally want to talk about this dot product, which I think everybody enjoys, the dot product. Okay, so say this vector that we've been studying for so long, we call it ket v. That just means a column vector named v. So I'll write it over here. Say ket v, this column vector named v is x, y, which we also write like this, x component in the 0 direction and y component in the 1 direction. And let's say we're holding on to this vector, and I really want to know what is x. Well, you might say it's x. Just look at it. But another way we can get at it is by doing like the dot product of the 0 vector and v. And remember, this 0 vector, that's like 1, 0. And what is that? You probably remember from linear algebra. You can write it like this. 1, 0 is like a row vector times x, y as a column vector. That's like 1 times x plus 0 times y. That's the dot product, which is x, which is what we're looking for. Or like, in paths diagram notation, if you still remember about that, it's kind of like we're doing this. 1, 0, and we're getting x down here. X plus 0. Yeah. By the way, this is actually a 1 by 2 matrix times a 2 by 1 matrix, so it results in a 1 by 1 matrix. But it's a fact of life in mathematics that you can freely typecast between 1 by 1 matrices and numbers. It's a little bit weird. So if you ever end up with a 1 by 1 matrix, you can be like, that's just a number. Here, what happened is to do this dot product, we left v as it is, and we turned 0, which is this vector, into a row vector, and then we multiplied. And there's some notation for turning things into a row vector, which I'll now tell you. This is the second half of Dirac's ket notation. So here, this row vector 1, 0 is the vector or the matrix transpose of 1, 0. It's like turning it on its side. And in general, AB is the dagger or the transpose of the column vector AB. Oops. This is if all these numbers are real numbers. If they're complex numbers, you should put in complex conjugations, but we're not doing that. Yeah, so Dirac had some notation for this. This is like Dirac's bra notation. By the way, it's like bra is going to be a row vector, and like ket is a column vector, and like bra ket is like bracket. That was the joke. You're supposed to laugh. No, this is like, I don't know, Dirac thought this was funny, so that's why he called them these things. This notation, like the backwards angle brackets, which we haven't seen before, but we are seeing it now, this is just defined to be the conjugate transpose, the dagger of v. Or basically, it's the row version of v. Row vector version of v. Okay, so like this notation just means like type is row vector. But if two things have the same name, it means like one is the row vector of the other. And row vectors are called bras. Although mainly we talk about kets. Okay, so in general, now that we have this like somewhat goofy notation, but it's good notation, even if the name is sort of dumb. Okay, so if you have some other vector, let's say f ket, that's a vector, and let's say its coordinates are a, b, then the dot product, or inner product, of f and v, these two vectors, is, well, you take the row version of f, and you multiply, that's a 1 by 2 matrix, by the column version of v. That's a 2 by 1 matrix. So it's like AB times x, y, which if you remember the rules for matrix multiplication is ax plus by. Okay, that's the dot product of vector f and vector v. And the last component of Dirac's notation is like you just delete this dot symbol and like one of these vertical bars. And you just say, in order to save symbols, I'm going to write this like that. Okay, so that's the last component of the notation. And these things are all the same thing. And that's the number, that's the dot product of ket v and ket f. Okay, so as little examples, suppose we were to do the dot product of ket 1 and vector v. Well, this is the row version of ket 1, which is 0, 1, times the column version of v, which is this vector we're calling x, y. And that's 0 times x plus 1 times y, it's y. Okay, so dotting a vector v with ket 1 gives you out its second coordinate, or some might say first coordinate. So if we do, we can summarize this by saying if we do, extract on ket v, a qubit in state ket v, which is x 0 plus y 1, then the probability that the display is 0, well, we know it's x squared, but now I want to write that as the inner product between ket 0 and v squared. And the probability that you display 1 is the inner product between 1 and v squared. Okay, so in some sense, it's like if you have a qubit state, and that state is the vector v, ket v, and you maybe don't exactly know the coordinates of v per se, this is sort of like a formula that tells you how the extract probabilities work. It's the square of the inner product of like the thing you're taking the outcome with. And I might add that like this, we talked about 2 dimensions here and like 1 qubit, but this holds, in general in higher dimensions. I'll write it over here. So like similarly, if let's say ket w is like a 2 qubit state with like amplitudes A, B, C, and D, then what is this? Bra 1, 1 times ket v. It's the inner product of ket w with bra 1, 1. So 1, 1, remember, is 0, 0, 0, 1. So this is 0, 0, 0, 1 times, and then w is just this. It's like A, B, C, D. So this is matrix multiplication. It's a dot product. It's D. And D is really the amplitude of w on 1, 1. Like, remember, this is like 0, 0, 0, 1, 1, 0, 1, 1. So this is the amplitude of w on the basic state 1, 1. In particular, it means like if you do extract all on w, if you do extract on state w, like the probability that you see 1, 1 in the output is d squared, which is this inner product squared. Okay, so that's kind of the general rule for how measurement works. The probability of seeing a particular measurement outcome is the square of the dot product of the state and the outcome vector. Any questions about this? Okay, so in some sense, like that's one reason you might want to compute a dot product, because it tells you, like the dot product of a general state vector with one of the basic state vectors, the square of that dot product tells you the probability you'll see that when you do a measurement. But before we ever did quantum computing, we did linear algebra, and for some reason in linear algebra they tell you about dot products. And why? Why do you normally compute the dot product between 2 vectors? Why would you compute that number? So like, why this? So like the inner product between, or dot product between ket f and ket v is this number. What is the meaning of this number? Well, let's figure out why dot product. Okay, so this is about the dot product of v, which we have depicted on the board here. This is v. Let me make this other thing f, and I'll make it like, I don't know, here. Let's say this one is f, ket f, and it's a, b. Okay, so here are my two vectors of interest, v, which is xy, and f, which is ab. And, I drew it down here in my diagram. Let me copy my notes so I don't mess up. Let's say f is actually down here. Okay. So I did this because I want to give a name for the angle for f. I'm going to call it alpha. So I don't know, maybe that's like 10 degrees or something. Okay, so say this new vector ket f is a, b. It's at angle alpha. So in other words, we could call it rotation sub alpha applied to ket 0. Because ket 0, remember, is the horizontal thing. Okay. And, in the same way we have this, this rotation by alpha, its matrix is a, b, and negative b, a. Okay, so this column is where ket 0 goes to. It goes to AB when you do rotation by alpha angle. And this is where ket 1 goes to when you do rotation by angle alpha. So it's like over here. This is also alpha. And let me call this vector ket G. And as we know, it's negative B, A. Okay. So let's call this column ket G. Okay, now if we think about this dot product, it was like the bra version of f times the ket version of v. So let's look at the bra version of f. The bra version of f is a, b. This is like the dagger, the conjugate transpose of f. And f is rotation by alpha applied to the vector 0. Okay, so the bra version of f is like the bra version of this. And now, as like a side note, I have to remember for you some fact kind of from linear algebra or path diagrams. Let's say K and L are two matrices. K and L are two matrices, which might be vectors. And we take their product, and then we take the transpose. This is equal to L transpose times K transpose. And why is that true? Actually, you remember a matrix is the same thing as a paths diagram, right? And like matrix multiplication is the same as gluing two paths diagrams together. And this dagger, this transpose, is the same as reversing all the arrows or turning the picture upside down. So this is like you glue K onto L and then turn everything upside down. That's the same as turning L upside down and gluing it onto the upside down version of K. Okay, so that's why that's true. And we're going to apply this little fact right here, where like I guess this is K and this is L. So what I'm saying is this is 0 transpose times rotation by alpha transpose. And this is bra 0. And this is like the opposite of rotation by alpha. It's the undo, because this is a unitary. So this is rotation by negative alpha. Or we can just say like this is like the transpose of this, which we saw is like the opposite rotation. Okay. And therefore, I'm trying to answer why dot product, why compute this f times v. So this inner product of f and v, or dot product of f and v, is bra f, which is this. So it's 0 times rotation by negative alpha times v. Okay, so that's what that inner product is. But Now we can look at it differently. We can parse this as like bra 0 times this vector. This is rotation of v by negative alpha degrees. So if we go back to this picture where this was v, rotation of v by negative alpha degrees is like taking this red vector and like going clockwise alpha. So that means it's kind of like here. This is alpha. This would be like rotation by negative alpha applied to v. Sorry, this is a bit messy. And so that's that vector. And also, what does it mean to take like, bra 0 times a vector, 1, 0 times some mystery vector? It just picks off the first coordinate. So in other words, like this is the 0th coordinate, if you will, or first coordinate of this vector. Okay, so the point of all this has been to understand what the dot product means. And let me redraw this picture now. Like think of this, okay, this diagram's kind of gross, but like think of this as like the original picture. And now let's think of the world where we rotate by negative alpha. Rot minus alpha world. So now, like, v is gone, if alpha, let's say alpha is like 10 degrees. Alpha is, like, v has gone like 10 degrees clockwise. So maybe now this is rot minus alpha v. This is now like rot minus alpha of f. It's now horizontal. And this, oops, it's like rot minus alpha of g, like it's now vertical. And this inner product, this dot product, is just like the horizontal component of rot minus alpha v, which is like this. This is like the 0th coordinate of rot minus alpha v. Or like back in this picture, it's this length. Okay? So to summarize, finally I'll write here the glorious summarization of dot product. The dot product of two vectors is like the length of one of the vectors when projected onto the other vector. Okay, so the summary is that f inner product v is, it's got several interpretations. It's kind of like v's coordinate on f in the like fg basis. Right, so if you think of like f and g as like a different coordinate basis, then like it's like what is this vector's f coordinate? Or you might say it's the length of v's projection onto f. This is all for unit vectors, I should say. Here, everywhere, I'm assuming that ket f and ket v are unit vectors. Or you could say it's like the sine of gamma, where gamma is the angle between these two vectors. Oh, sorry, cos. I keep mixing these up today. Angle between v and f. Okay, because that's like the meaning of this 0th coordinate, or the meaning of cosine. It's like the cosine of this angle is that horizontal coordinate. Okay, and like similarly, g inner product v would be like the length of v's projection onto g, which you could either say it's like the cos of like the angle between v and g, or it's like the sine of the angle between like V and F. Okay, and all this extends to higher dimensions. So these are all two-dimensional vectors, but in general, even if you have like, d-dimensional vectors, if they're unit vectors, the dot product between them is the cosine of the angle between them.